Okay, hello everyone. My name is Florent Lebeau. I am an application and support engineer here at Allinea. And today I'm going to present to you how to increase code vectorization. Let's just start with the presentation. So here is the outline for this presentation. I will start with a short introduction about what is about vectorization and why it is important, and especially on the latest architectures. And then I will illustrate how Allinea tools can help you to find out when and how to vectorize your applications. So first, let me say a few words about where vectorization comes from in terms of hardware. So here is an illustration of a CPU. In a CPU, you will find cache memory. It is a very fast memory for the processor. You will find a control unit as well. These control units are now very complex. It enables to manage the instruction execution and perform things such as a very complex mechanism such as branch prediction, out of order execution. And the other parts of a processor consist in the cores. So the cores are really the compute parts of the CPU. Today, the CPUs are many cores. So typically 2 to 8 cores, for example, on desktop CPU. Here I'm showing an example with 4 cores. So parallel programming models consist in taking advantage of this core to distribute processes or threads in order to accelerate and execute instructions faster. Inside these cores, you will find another level of cache memory and 2 types of compute units, vector and scalar units. As the name indicates, while a scalar unit is able to process one element at a time in order to execute an instruction, for example, square root, the vector unit is able to process many of them in a SIMD fashion. So SIMD stands for single instruction, multiple data. So the same instruction will be applied to all these elements at a time. The vectorization capability depends on the hardware. And for example, Intel Haswell processors have a 256-bit wide vector unit that enable to process 8 single precision elements or 4 double precision elements at a time. The forthcoming Intel Knights Landing processors have a 512-bit wide vector unit that enables to process 16 single precision elements or 8 double precision elements at a time. So now that we understand the hardware mechanism of vectorization, how can we check that this is used in a real application? Here is where Allinea Performance Report can help. This tool provides you with an explicit and usable output that will describe the behavior of the application and if vectorization is used or not. To get started with Allinea Performance Reports, you don't need to recompile your code or use any kind of instrumentation. You just need to use your existing binary. The use of Performance Report results in a very low overhead. The behavior you see in the report is not disturbed by the tool itself. And you can integrate Performance Report very easily to your workflow. And I would like to illustrate that with a real application called NECT 5000. So NECT 5000 is an open source code developed by the University of Chicago and Argonne National Lab. It is written in C and Fortran and relies on MPI for parallelization. You will be able to find more information on this application by following the link on the screen. And I suggest that now, let's see how to find out if this CFD code takes advantage of vectorization on a two-dimensional Navier-Stokes test case. So here is the original job script for my test case. We are running NEC 5000 on one node using 8 processors. And we are executing the application using the srun slurm command. As said earlier, performance report is very easy to use. You just need to prefix your srun command with the command perf-reports. So when this is done, you can just submit the job. NEC 5000 will run as usual, but performance report, of course, will run in the background. And when the job is complete, 2 identical report files are generated. So you have one version of the reports in a text file, in text format, and the other one will be in HTML. So let's have a look now at the HTML report from NEC 5000. And you can find different sections in this report. The header on top of the report contains information about the configuration of the job, the number of processes you're using, the number of nodes, and the execution time. And below this header is a summary that indicates where most of the time is spent. Is the application mainly performing computation, communication, or IOs? For each of these aspects, you will find the corresponding percentage of the application time, as well as advices if these values are abnormally low or high. In this case, NEC 5000 is compute bound, which is good. We are taking advantage of the available compute resources. In the bottom of the report, you will find different boxes that give more details about the computation, communication, or IOs. In our example, we are interested in getting more information about the CPU operation. So, as you can see, we can quickly figure out that 23% of the computation time is spent in vector instructions. So to improve CPU efficiency, Performance Report invites us to use a profiler and check the compiler's advices to identify time-consuming loops. But before doing that, let's suppose to understand why vectorization is important. So you have to know that the newest generation of CPU architectures don't increase the frequency as they used to in the past. Instead, the number of cores in processor has been multiplied. As a result, if your code doesn't take advantage of vectorization or parallelism, the upgrade of the hardware won't give any performance. It is only by modernizing your code to use vectorization or parallelization that you will get performance. But using both vectorization and parallelization will enable you to fully use the potential performance of these new CPUs. So when do we need to spend time to achieve IO vectorization? This is where a profiler such as Allinea map is useful. With a profiler, we want to identify the time-consuming sections of the code. To retrieve this information, we just need to recompile the code with -G. Similarly to performance reports, the use of map results in a very low overhead. the profile generated is not disturbed by the tool itself. Allinea Map is easy to use. You can analyze the behavior thanks to your user-friendly interface, an interface that enables you to get a deep understanding of what your application is doing over time. So, in order to profile NEC 5000, we just need to recompile with -G and edit the job script to prefix the srun command or MPI run command alternatively with map-profile. When the job is submitted, the application runs as usual. Map runs in the background and will provide a .map file that corresponds to the application profile. You can open this file in Allinea Map's GUI afterwards in order to display the results. And here is the profile of NEC 5000 on our test case. You can see the metric view on top of the window. The timeline you see describes the amount of time spent in computations in green, communications in blue, and IOs in orange, following the horizontal axis. The vertical axis corresponds to the different processes of our application. The window in the middle makes the link between this timeline and the source code of the application. As you can see, the code is annotated to indicate how much time is spent in a particular line of code and the nature of the operation performed, computation, communication, or IOs. The window in the bottom of the GUI summarizes the time spent per function and in their order of execution in the stack. So this gives us a general understanding of the application. But what about vectorization? Well, the metric window on top of the GUI can display further information such as CPU instructions, and this is what you can see on the screen. This is where we will be able to see the amount of vectorization over time. You can see here that vector instructions are executed during the whole run. The call stack view in the bottom of the GUI enables us to find out the corresponding function in the source code that make use of vectorization. So as a result of this profiling, we can easily identify MXM16 as the bottleneck of our application here. So MXM16 is one instance of different MXM functions that all correspond to matrix multiplication functions. They are all defined in the same file called mxm_std. The total amount of time spent in these different functions in this file correspond to about 30%. So the question we have here is, these functions are obviously vectorized, but are they vectorized enough? Let's follow Performance Report's advice and have a look at the compiler output. As we have identified one file as the main bottleneck, we can recompile it in order to generate a vectorization report. On this version, we are using the GNU compiler, and we can use the -f3 vectorizer verbose flag to provide us with a report. Analyzing the report generated show that 141 loops were vectorized in this source file. But can a different compiler vectorize better? On my system, the Intel compiler is also available. So I can recompile the code to generate a similar report using the -qopt report base vec flag instead. The analysis now show that 542 loops have been vectorized. But will this impact my simulation? This is an answer that I can get using Allinea tools. So the first thing I can see is the execution time. It is now 68 seconds using Intel compiler compared to an initial runtime of 108 seconds when using GNU compiler. The CPU metrics of their reports show that 31% of the time is spent in vector instructions compared to the 23% of the initial version. Allinea map enables us to check the bottleneck of the new executable and displays the answer very clearly. MXM remains the main bottleneck. So we managed to increase the vectorization of this code by changing the compiler, but can we increase the vectorization even more? So let's pause to explain how you can increase the vectorization of the code. At this point, we have noticed that different compilers have different capabilities. But here are some guidelines that you can follow in order to ensure that vectorization is performed. First thing, due to the SIMD nature of vectorization, remove the conditional inside the loops. Conditionals will make the code to be serialized in order to execute the alternatives one after the other. Second, make sure that the loop count is known so that the compiler can execute vector instructions in a known number of batches. Third, pay attention to how your data are stored. Vectorization is efficient when performed on contiguous sections of memory. 4, make sure that your data are independent in order to execute SIMD instructions. And final point, guarantee the SIMD nature of loops using compiler directives. So to illustrate that, I have written my own version of matrix multiplication to show you how you can improve the vectorization of your code using Allinea map. Here is the corresponding profile of my matrix multiplication, and as you can see, more than 80% of the execution time, 96%, is spent in one line of code, line number 63. Map indicates here that vectorization is non-existent. If we analyze how the data of the matrix B are stored, we can see that the J variable corresponds to the contiguous elements of the array. However, J is the iteration variable of the outer loop of my matrix multiplication. This breaks the vectorization. So to optimize this, we can use the transpose version of B instead and switch the indexes. K now correspond to the contiguous elements of the array instead, and the K also correspond to the inner loop of my multiplication. And as a result, vector instructions can be performed efficiently, and we can see the results on the execution time and the timeline. In NEC 5000, this MXM is already well optimized, and optimize it further is not that straightforward. But fortunately, math libraries exist. BLAS, LAPACK, Intel MKL libraries are optimized, very optimized, and maximize the vectorization to perform traditional linear algebra operations such as matrix multiplication. So to improve the vectorization of our code, we are going to replace the calls to the MXM with calls to the MKL's dgem instead. This is something that has already been implemented in NEC 5000 and can be done easily by recompiling the application with a specific flag. So we recompile the application using this dblas_mxm flag, and we link the executable with the sequential version of the MKL library. We can generate a report from this version and check that vectorization has increased indeed, from 31% in the previous run to 40% in this version. We have accelerated the compute part of the simulation so much that the profile is quite different. We are almost spending as much time in computation than in communication. Performance reports indicate that there is an MPI imbalance, and the use of a profiler confirms that. Our new bottleneck now corresponds to an MPI all-reduce function because of a too small amount of computation. This behavior leads us to reconsider the test case and prefer a larger simulation on many nodes, for instance, if we want to go on with the simulation, with the optimization. Sorry. So this leads me to the conclusion of the presentation. I hope you enjoyed it. So to recap what we've said today, I showed that vectorization is a difficult task, but tools such as Allinea performance reports and Allinea map make it easier. With performance reports, you just need the application binary. You can identify quickly and easily if an application makes good use of a vectorization. And with Allinea map, you can inspect the vectorization of the application over time and easily identify the application bottlenecks and candidates for vectorization. So it's now time for our Q&A session. Again, if you have questions, please send them directly to Mark Clark directly in the chat window. So Mark, do you have questions so far? So yes. So there's a question, why is the -02 optimization flag being used instead of 03? Well, that's a good question in that case. Actually, to tell you the truth, there are some files of Net 5000 that are compiled with -02 and some other files compiled with -03. This is something that I've not investigated. There are reasons why less aggressive optimization flags are preferred, and one reason, for example, can be the precision of the results. If there are strong constraints on the precision, you may prefer a less aggressive optimization flag. So you may prefer 02 versus 03. Okay, so I guess it is the case. It is the case here, and that this is something that has been taken into account by the developer of the application. But very, very good question. Very interesting question indeed. Are there any other questions so far? Okay. So yeah, there's a question about the slides that were presented, if it is possible to share them to the attendees. So this is indeed what we are going to do. So my colleague Mark will get in touch with you all to share the slides with you. So if you ever want to share them with your colleagues afterwards you are of course more than welcome. So I prepared a few questions myself to go on with the discussion, and one of the questions that are frequently asked by people is, how do map and performance reports collect data? So you have to know that indeed profilers can use different techniques to collect information. There are two main differences among profilers. Some profilers are doing tracing, some other profilers are doing sampling. So tracing consists in collecting information about everything that the application is doing, generally by relying on instrumentation. Sampling, on the opposite, just collects information at regular interval of time. So map and performance report rely on a sampling technique. But more than that, it is statistical sampling where the sampling rate is automatically adjusted to the length of the run. So we make sure, by doing this, we make sure that we keep the overhead to a minimum and that the output, the profile that is generated, is as lightweight as possible. Of course, if you want to retrieve more details, maybe in your application, and sample more frequently, this is something that you can do by specifying, for example, the sampling interval manually, so in microseconds using an environment variable. So you can force this, but of course you have to keep in mind that if you do this, you may increase the overhead, of course, of the profile. And then a second question that is frequently asked is, how are the data about vectorization collected? So vectorization operation are actually collected, well, these information are collected from the operating system. So we basically sample files from the OS kernel to have a look at the instructions that are executed, and we perform statistics on them and restitute them in the profile. So if you ever want to get more details on which instructions are counted as vectorized instructions, you can have a look on our websites. So I'm sharing with you our user guide online. So you will see in this section of our user guide, you will find the list of all the instructions that are taken into account and reported as being vectorized instructions. So this is something that you can read if you want to know more about this. Okay, so there is a question about performance reports in the DDT 4.2.1 version. Do we need to purchase it separately? So indeed, let me clarify about this. So performance reports and Allinea map are two separate products. And I see that you are using quite an old version of DDT. So at the time, I think, so at the time it was DDT and map were separated. So basically there is one package, one installation package for both DDT and map. So DDT is a debugger and map is the profiler that I just showed in my presentation. So these two tools are gathered into one name called Allinea Forge. So you download Allinea Forge, and basically with this installation package you have access to both. Now, the license that you have may enable either DDT, either map, or both. Okay, so these products are enabled by your license. Performance reports is a separate installation package. And same thing, you can use performance reports if your license enables you to do so. So similarly, you can have one license file that enable everything, DDT, map, and perf reports, or a separate license file for these different products with different characteristics, maybe different numbers, a different size, license size for all of these products. Everything is possible, basically. It's very flexible. But from your question, so does my version of TDT enable me to use performance reports? No. You will need to download performance report separately from our website. So let me show you where to find this different package. So if you go on our main page, so you have two tabs, Developer Tools and Performance Reports. So the Developer Tools tab will enable you to download Allinea Forge. Okay, so if you go to the download link here, this is where you will find the packages. Okay, so just select the package that corresponds to your platform. Okay. Similarly, for performance reports, you will find similar page, and if you go to download, again, you just select the package that corresponds to your distribution. But these are two separate installation packages. Okay. And this leads me to how to request for a trial, for example, if you want to try a map, a perf report, and your license doesn't allow you to do so. So on our website, you can go to this trial page, start a trial, and you just need to fill the form online. You will receive a license straight away. By default, this license allows you to use up to 64 processes and for a week. But of course, if you need a larger license, if you need more time to evaluate our products, our sales executives will get in touch, try to understand what are your needs, and we'll be happy to extend it to your needs. Right, so feel free to make a request. So there is a question now about debugging. Is it possible to debug the vectorized section of the code on the instruction level? So this topic is related to debugging, so it's a bit different from our scope, but yes, it is possible with Allinea tools. So as I said, map is a part of Allinea Forge, and Allinea Forge includes map and DDT. And indeed, this is going to be possible with Allinea DDT, our debugger, when you can indeed debug vectorized sections of the code, and you can view the disassembly, for example, of the executable, and analyze for a particular line of code. You can visualize the corresponding instructions in the binary. So yes, this is possible if this is something that you feel comfortable with, of course, because this is not as straightforward as that. This is of course possible in the debugger. So there is another question about the support of KNC. Does performance reports support KNC? Well, that's a good question, actually. I am not sure. The best thing to do, if you have a question regarding the platforms that are supported by our different products, this is an information that you can find on our website. So typically, for example, for this case, I'm going to have a look at the performance report page, and you will find this platforms link here. And you will see the different platforms. And here, indeed, the supported platform is only x86-64. Okay, so indeed, it does not support Knights Corner. Yes, indeed, there is no package, no separate package for the KNC for perf reports. Yes, that's true. So there is another question. Is it necessary to use preprocessor directives like SIMD, or would the compilers automatically vectorize loop with -02 or -03? Well, no, it is not. It is not necessary. It is something that you would need to do if, for example, you know that a loop can be vectorized, but the compiler doesn't detect that this is vectorizable, basically. So the compilers are a very complex mechanism to detect dependencies, for example, but sometimes, of course, it is somehow limited, and sometimes these directives, such as OMP SIMD, enforce vectorization to be performed in saying to the compiler, don't worry, this is, for example, data independent, you can vectorize safely. Okay, so this is the case where you would need those directives. Otherwise, for, I would say, most cases, the compiler is able to vectorize with a flag like -02 or -03. Yes. So there is a question as well about, so does the programmer need to explicitly adapt the code for vector bit size of the processor, for example, with Aswell or Knights Landing? Well, no, really. This is something that is done automatically by the compiler. As long as you show, if you want that in the code, that this is code, this section of code can be vectorized, the compiler will turn it automatically into the corresponding instructions. So to take advantage of the 256-bit wide vector or 512-bit wide vector units. Okay, so for the programmer, basically the work remains the same. It's just specifying or showing in the code that this can be vectorized. The work, the adapting to this or that vector size is the work of the compiler, and this is done automatically. So I don't think there are more questions. So let me thank you all for your attention. As I said, my colleague Mark will get in touch with you to share the slides of the presentation, and we'll probably ask you for some feedback. And that's it. So thanks a lot again. Thanks a lot for your attention, and have a good day or a good evening. Bye.